this video, we'll talk about rational zeros of polynomial functions. We'll be talking about long division and the division algorithm, remainder and factor theorems, synthetic division, and the rational zeros theorem. Let's start off with some polynomial long division. We're going to use long division to find the quotient and the remainder. First, we need to set it up. On the outside of the division problem, we put the x squared plus x plus 1, and on the inside, we put 2x to the fourth plus x to the third, and then we need some placeholders. So we have 0x squared plus 0x minus 3. You need to have those placeholders in there so that you can do the division correctly. So we start off with x squared. X squared goes into 2x to the fourth. How many times? It would go 2x squared. 2x squared times x squared is 2x to the fourth. So 2x squared, we're going to line up with our x squared term. So we put 2x squared over there, and then we multiply. 2x squared times x squared is 2x to the fourth plus 2x to the third plus 2x squared. Draw the line and change the signs for each one of these. When you're doing division, you want to subtract, so when you're subtracting a polynomial, you change the sign. The first term will always cancel out. That's a minus 2x to the third and a positive, so we have a negative, that would be negative 1x to the third. Making a big mess there. And that was a plus, now it became a minus, so minus 2x squared. And we bring down the 0x. X to the third goes into negative x to the third, negative x times, and notice the x lines up with the x. Multiply, we get negative x to the third minus x squared minus x. Draw the line, change the sign. The first term will cancel out, and we get negative 2x squared plus x squared. We end up with a negative x squared plus x, and we bring down the negative 3, and x squared goes into negative x squared and negative 1 time, and again the terms line up nicely. Multiply, we get negative x squared minus x minus 1. Draw the line, change the signs, and we end up with 2x minus 2. So the answer is 2x squared minus x minus 1 plus our remainder 2x minus 2 over x squared plus x plus 1. Try this. Use long division to find the quotient of x to the fourth plus 3x squared plus x squared minus 3x plus 3 divided by x plus 2. Now, remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is f of k. I'll show you how that works. If all we want to do is find the remainder, what we can do is find f of negative 3. F of negative 3 is 2 times negative 3 squared minus negative 3 plus 12, which is 2 times 9 plus 3 plus 12, which is 33. So if we divide this out, we will come up with a remainder of 33. So why is this important to know? Because a polynomial function has a factor x minus k if and only if f of k equals 0. So it's a factor of something if the remainder is 0. At this point, I'd like to clarify a little bit of terminology. If we have a polynomial function, all four of these things are true. They are equivalent. We can say that x equals k is a solution or a root of the equation f of x equals 0. We can say that k is a 0 of the function f. We can say that k is an x-intercept on the graph, or we could say x minus k is a factor. All four of these mean the same thing. Now we're going to look at synthetic division. We put the 1 over here in our little box, and then we just use the coefficients. So we have 3, negative 2, 1, negative 5, and the way I do it is to draw a line here and then another line to give us our remainder in this box. This 3 comes straight down, and then we multiply. 1 times 3 is 3. We add 3 minus 2, 3 plus a negative 2, and we get 1. 1 times 1 is 1. Adding again, and we get 2. 2 times 1 is 1, and we add, and we get, 2 times 1 is 2, and we add, and we get a negative 3. So the quotient is 3x, we go down 1 from our original, so it's 3x squared plus x plus 2 plus negative 3 over the divisor x minus 1. Try this one. Remember that when you're doing synthetic division, because we have a plus 2 here, it was supposed to be an arrow, because we have a plus 2 here, we need to have a negative 2 as our divisor. We're now going to look at the rational zeros theorem. Rational zeros meaning any zeros that are either whole numbers or can be written as a fraction. So if we have a polynomial and the polynomial is in this form, and if we have a rational zero, p over q, then p is a factor of the constant coefficient. So p is a factor of this, and q is a factor of this. I'll show you how we use that. If we want to find the rational zeros of f of x equals x to the third minus 3x squared plus 1, by the rational zeros theorem, we look at the leading and the constant coefficients. In this case, the leading coefficient is 1 and the constant is 1. Therefore, if we're looking at potential zeros, it's going to be positive 1 over 1 or negative 1 over 1. Those are the only factors of 1. So all the rational zeros are either 1 or negative 1. So these are the potential zeros. Then we need to check and see if they are actually zeros. So let's put them in. If we take f of 1, we have 1 to the third minus 3 times 1 squared plus 1, which is 1 minus 3 plus 1. 1 minus 3 is negative 2 plus 1 is negative 1, which does not equal 0, so this is not a 0. If we look at f of negative 1, we have negative 1 cubed minus 3 times negative 1 squared plus 1. This is negative 1 minus 3 times 1 plus 1. So here f of x is equal to negative 3. Again, sorry, that was f of negative 1 equals negative 3. Again, not a 0. So neither one of these are zeros. So this function has no rational zeros. Let's take a look at the graph of it. If we put this equation into our calculator and graph it, we can see that it has 3 intercepts. And if I zoom in, here's another trick on zooming. A Z box lets you make a box to zoom in on. Enter, make a little box there. So I've got 3 zeros, but none of them are rational numbers. A little later on, we will be looking at the real zeros, but for right now, we are just looking at the rational zeros. Finding the rational zeros. To find the rational zeros of f of x, first thing we want to do is look at the leading coefficient and the constant coefficient. So the leading coefficient is 3. The constant coefficient is -2. So we've got several potential rational zeros of f. So the first thing we need to do is look at the factors of -2 and divide that by the factors of 3. Factors of -2 are plus and minus 1, plus and minus 2. Those are the factors of -2. The factors of 3 are plus and minus 1 and plus and minus 3. So the potential rational zeros are plus and minus 1, plus and minus 2, plus and minus 1/3, and plus and minus 2/3. We're going to take these numbers and we will now graph that function. So I have this function in the y equals. I graph it. I've graphed it and I've zoomed in on it. And from here we can see that the zeros look like -2. A potential one would be -1/3 and +1. So the next thing we need to do is to use synthetic division to factor it and find the zeros. So we're going to be looking at -1, -1/3, sorry, that was -2, -1/3, and a +1. So what we want to do is to choose any of these for synthetic division. So I'll choose the -2. -2 will go in there, and 3, 4, -5, -2. 3 comes down, -6. Adding them, I get a -2. -2 times -2 is a +4. -1, +2, 0. That tells me that is a 0. So that one of my factors is going to be x plus 2. And then the remainder here is going to be 3x squared minus 2x minus 1. And I can factor that. I could use synthetic division again with these others, or I can just go ahead and factor this. 3x and x, 1 and 1, and I want a -2, so it's a -1 and a +1. So there are my 3 factors. So x is going to be -2, -1/3, or +1. So all 3 of these are rational zeros. Try this. Use the rational zero theorem to list all the potential rational zeros of f of x equals 2x to the third minus 5x squared minus 5x minus 1. Then use synthetic division and factoring to determine which ones, if any, are 0. I forgot to say that you want to graph it in there. First use the graphing, then the synthetic division factoring. And now, just for fun, a little bit of factoring. See you in class.